Hello everyone, welcome to our report on multiple states models. In this presentation, we will explore how these models work, their application, and why they are essential in understanding complex systems. So join us as we break down the key concepts, examples, and practical uses of multiple states models.
The single decrement model is used to analyze situations where individual transitions from one state to another due to a single cause. In life insurance, these states are typically alive and dead. The model solely focuses on the transitions from alive to dead without considering other possible transitions. A key component of this model is the force of mortality, denoted as mu sub x. These represent the instantaneous rate at which individuals of age x are expected to die. It's a measure of likelihood of death at a specific age. To determine the probability of an individual age x surviving an additional time t, we use the following formula. This formula integrates the force of mortality over the time period t to determine the survival probability. Conversely, the probability of dying within time t is this formula. This is simply 1 minus the survival probability, giving the cumulative probability of death over the period. This model is foundational in calculating the life insurance premiums and reserves, as it helps actuaries estimate the likelihood of death for policyholders at various ages.
Next, we have the double decrement model, which is used to analyze scenarios where an individual can exit a state due to one of two competing risks. In this model, we focus on two main aspects. First is identifying the two competing risks, such as accidental death and death from other causes. For example, in life insurance, a person can die due to accidental death or natural causes or other reasons. This model helps actuaries determine first the time until an individual exits the initial state, and second is which of the two possible decrements occurs. This diagram illustrates how the double decrement model works. At state 0, it represents an individual who is alive, and there are two possible transitions from this state. First is the state 1 or the accidental death, which occurs at the rate of mu sub x plus t, first decrement. Second is the state 2 or the death from other causes, which occurs at the rate of mu sub x plus t, second decrement. First, we have the total force of decrement, which is the sum of these rates. This means that at any given time, the probability of leaving the initial state is based on the combined effects of both causes. Next, we have the occupancy probability, which is the probability of remaining in the initial state, which is given by this equation, which tells us the likelihood that an individual is still in the initial state after a given time. And lastly, we have the transition probabilities, which determine the probability of moving from state 0 to state 1 or 2, given in here in our equation. These equations help us estimate the probability of each specific characteristics of the model. First, we have that transitions are irreversible, that once an individual moves to another state, they cannot return. For example, once someone passes away, they remain in that state. Second is that no need to track post-decrement transitions, that after an individual transitions, we stop tracking their status. This simplifies the model and makes calculation more efficient. Lastly, we have the withdrawal model diagram, that instead of tracking death due to different causes, this model tracks whether an individual withdraws from the system.
Now let's talk about the disability income model. The disability income model examines scenarios where individual can transition between multiple health states, particularly focusing on disability and recovery. The primary states considered are healthy, disabled, and dead. Transitions between these states include from healthy to disabled, from disabled to healthy, from healthy to dead, and from disabled to dead. Transition between healthy and disabled are reversible, as individuals can recover or become disabled again. But transition to the death state are irreversible, as there is no return from death. Between states has an associated intensity or rate, similar to the force of mortality in the single decrement model. For example, mu sub 01 of x is the rate of moving from healthy to disabled at age x. Next is mu sub 10 of x is the rate of moving from disabled to healthy at age x. Next is mu sub 02 of x is the rate of moving from health to death at age x. Mu sub 12 of x is the rate of moving from disabled to death at age x. This model is crucial to insurers offering disability income products. It helps in determining appropriate premiums based on the likelihood of disability, recovery, and death. It also aids in setting aside funds to pay future disability benefits considering the probability of various transitions.
So now, I'll introduce you to discrete-time Markov chains. A Markov chain is a mathematical model used to describe systems that change over time. So the key principle is that the next state depends only on the present state, not on how we get there. So the figure in the screen represents a discrete time Markov chain where the state variable y sub t moves between a finite set of states e, which is equals to 0, 1, and 2 at discrete time steps. So in insurance, this can model a policyholder's health. So 0 if healthy, 1 if disabled, and 2 if dead. So the probability of moving between states help insurers predict risk, claims, and premium adjustments for better financial planning. So next is the transition probability matrix. So the matrix P sub t on the screen represents the probability of moving from state I at time t to state j at time t plus 1. So each element of matrix P sub t corresponds to the probability y sub t plus 1 is equals to j such that y sub t is equals to I, where I and j are the states which is healthy, disabled, or dead, and P sub t raised to ij represents the likelihood of moving from state I to state j at time t. So the total probability of transitioning from one state to any possible state, including staying in the same state, must always sum to 1. So this ensures that every individual in the model must move to some state at the next time step. Next is the Markov property. So the Markov property states that the probability of transitioning to a future y sub t plus 1 depends only on the present state y sub t and not on any past states such that y sub t minus 1, y sub t minus 2, and so on. So mathematically, this is expressed as the formula on the screen. So this property means that once the present state y sub t is known, the history of how the system arrived at y sub t becomes irrelevant in predicting y sub t plus 1. So we can conclude that the system is memoryless.
Now, let us discuss the difference between homogeneous and inhomogeneous Markov chains. So we say that it is homogeneous when P is constant with time t, which means that the transition probabilities do not change over time. Example of this is a weather model with fixed transition probabilities. And in contrast, it is said to be inhomogeneous when P is time dependent, which means that transition probabilities change over time. For example, let us consider a Markov model of employment where state 0 is working, state 1 is retired, and state 2 is deceased. The column represents the next state, while the row represents the current state. So, an absorbing state is a state that once entered cannot be left. And in this example, the absorbing state is state 2 or deceased. As you can notice, all elements in the row except the one in the main diagonal are 0. This structure ensures that once a Markov chain enters absorbing state, it cannot transition to any other state. Hence, all transition probabilities to other states are 0, and the only non-zero element is the self-transition probability of 1.
So for this topic of Lesson 9, we have the Chapman-Kolmogorov Equation. It provides a mathematical framework for understanding the probabilities of transitioning between different states over time. Thus, it can be determined by considering the intermediate states. So for the Chapman-Kolmogorov equation formula, we have t plus s px, which describes the transition probability from state x after a total time of t plus s, equals to tps, which describes the transition probability from time t to time s, multiplied by the spx plus t, which describes the transition probability from time s to time x plus t. Calculating APB of cash flows. So for this, we have two main kinds of cash flows associated with discrete time Markov chain. First is that we have the cash flow arising from being in a particular state, and then second, we have the cash flow arising from a transition from one state to another. So for the example, consider a homogeneous discrete time Markov chain with P equals to 0.4, 0.6, 0.8, and 0.2. The state space is E equals to the interval of 0, 1, and the subject in now in state 0, and I equals to 5%. So, for A, suppose that there is a cash flow of 1 for being in state 0 now and the beginning of the next 2 years. Find the actual present value of the cash flow streams. And for letter B, we have to suppose that there is a cash flow of 1 if transition from state 1 to state 0 occurs at the end of the first, second, and the third year. Find the actual present value of the cash flow streams. So for the solution of letter A, we have the probability of y sub 1 equals to 0 such that y sub 0 equals to 0, which is the initial state of 0, which is 0.4. Also, we have the probability of y sub 2 equals to 0 such that y sub 0 equals to 0, which is 2 times the quantity of the probability of the initial state. So we have the probability of 0 transitions to 0 plus the probability of 0 transitions to 1 to 0, which is 0.4 times 0.4 plus 0.6 times 0.8, which is 0.64. Thus, by the formula of the APB of the cash flow streams, we have 1.9615.
Hello everyone, now we'll talk about continuous time Markov chain. A continuous time Markov chain is a stochastic process where transition between states can occur at any time. In a continuous time Markov chain, we focus on transition probabilities which represent the probability of moving from state I to state J in time t. This helps predict how likely state changes are over time. This equation represents the probability that the system, which is in state I, at time u will transition to state J at time u plus t. For example, in insurance, transition probabilities help insurers predict risks, such as lapse rates or claims over time. Now we also consider occupancy probabilities, which indicate the likelihood of remaining in a state for a certain period. This equation gives the probability that the system remains in state I throughout the entire time interval u, comma, u plus t, and tell us how long the system is expected to stay in its current state before making a transition. For example, in insurance, occupancy probabilities estimate how long a customer stays in a particular state, which is important for pricing policies and managing reserves. Continuous time Markov chain rely on three key assumptions. First, the Markov property, which states that the future transitions depends only on the current state. This equation states that the future state y of u plus t depends only on the present state y of u and not on the past states y of b for any b before u. Second, the probability of multiple transitions in short time is negligible. Last, transition probabilities are differentiable functions of time. In summary, continuous time Markov chains provide a robust framework for modeling real-world processes with random state transitions. Thank you.
Now let's discuss calculating reserves. A reserve is the amount an insurance company sets aside to cover future claims. In a multiple state model, an insured individual can transition between different states like healthy, disabled, or dead. The reserve calculation accounts for these transitions. So the system of Yale's differential equation for a multiple state model is given as this equation. This equation describes the reserve dynamics for different states over time, incorporating premiums, interest, and transition rates between states. So this example is from the book of Lee and Long, which we'll be using in the example to compute for the reserve for an individual. Let's look at this example. This example also considers a disability income model, and we're asked to write down the system of Thiel's differential equations. We start by defining the reserve for state 2 denoted by this, which represents the expected future liability when the policyholder is in state 2 at time t. Now let's first analyze the case when the policyholder is in state 0. The exit rate is given as 8%. A premium of rate P is received continuously, but only for the first 10 years. The benefits for transition are given as the following. Using Thiel's equation, we derive the differential equation for the reserve in state 0, which you can see here. And expanding and simplifying this, we get this equation. Here, the indicator function takes a value of 1 when t is less than 10 and 0 otherwise, ensuring that the premium is only considered for the first 10 years. Now let's consider the case when the policyholder is in state 1. The exit rate is now 8.5%. The premium is payable, no premium is payable. The benefits for transition are the following. Applying Thiel's equation, we get this equation. Simplifying further, we get this equation. This equation models how the reserve evolves in state 1. So in this part, we will solve Thiel's differential equations numerically using Euler's method. Euler's method states that to approximate a function value at a future time step, we use its current value plus the product of the step size and the derivative at that point. Applying this concept to Thiel's equations, we approximate the reserve functions v0, v1, etc. at different time steps. For state 0, the reserve at the next time step is given by this. This means that the reserve at time n minus k plus 1 times h is approximately equal to the reserve at time n minus kh minus the derivative of v0 at t is equal to n minus kh multiplied by the step size h. Similarly, for state 1, we have this, which follows the same principle as before. So we begin with a boundary condition where the reserve at time n is 0 for all states. This serves as our starting point for backward recursion. From there, we can iteratively compute the reserve at earlier times using this. This means that at each step, we use the previously calculated reserve values to determine the next ones, moving backward in time recursively. And that wraps up our discussion on reserves.
And that wraps up our discussion on multiple states models. We hope that this presentation gave you a clear understanding of how these models work. Thank you for watching.